Hi, welcome back to our course on data structures and algorithms. This is Unit 3, which has been all about binary trees. Currently, we've been working through binary trees that are made with an array instead of with a linked data structure. What I'd like to do today is use an application of these trees. We're going to be making a heap. Specifically, we're going to be making a min-heap queue. Now, this is often called a priority queue, and you'll find that Java already has priority queues that we can use, but we're going to make our own today. We're going to make a min-heap queue. So let's get started. Starting with our new class, and this will be called min-heap queue. And we're going to import java.util.queue. And we're going to import java.util.abstractQueue. The abstract queue class is a class that does a lot of the kind of repetitive, annoying stuff for us and leaves some of the concrete implementation for us to do. So public class min-heap queue extends abstract queue. Well, let's take a look at what we have to do. I know it's going to tell me when it errors. It's going to tell me that I need to override some things, right? We're going to get that error for a while. Well, if we open up the documentation, here is the queue interface. Now, the queue interface has offer, pull, and peek, but also has add, remove, and element. And basically, these do exactly the same thing. You offer to the queue, you pull from the queue, or you peek at the queue. This is pulling from the front, by the way. But these do the same thing, but they'll throw an exception, so they'll make an error instead of returning false if you weren't able to add, or if say you tried to pull and it was empty, instead of getting an error, you'll just get null returned, and peek would be null. So these return a special character of false, null, null. This will actually throw errors. It just depends. Sometimes you want an error, sometimes you want a Boolean or a null. All right. Well, we're going to be implementing this interface using a subclass. So abstract queue implements this for us. And what we have to do is we have to do offer, pull, and peek. And then it will simply handle the other methods for us. Like, for example, we know the add method is the same as offer, but throws an exception if you are not able to offer. So we have to do offer, pull, and peek. But we also have to do size and iterator. But we're going to do a real basic iterator because iterators in a heap queue, not that interesting. So here we go. Well, we know we're going to be using a binary tree made out of an array, so let's make an array. I'll make an array of type object. I should make it private, though. Private object array. And I'll say public min heap queue. And let's say array equals new object of, we'll say type 5. Let's make this an expandable array so that we can expand as necessary. Make that a private method, private void expand. So we'll say object array, and I'll just call it temporary. And we'll get the length of our array, and we'll multiply that by 2. And then we'll loop through it. And we'll just copy them over. So now it'll be the exact same array, but twice as big. And then we need to make array, the pointer array, now point the reference that we have in temp. I want to point that over an array. Okay, super. All right, so we need to do the size method. Well, the way we're going to keep track of the size is with a variable. So we'll say private int size. And when the construction occurs, we'll start size as 0, which we know is actually default value, but I like to be explicit. You know that. Okay, we are going to be using generic, so I realize I'm missing those a little bit. Let's make sure we put those there. Okay, that's better. Okay, so let's write the size method. Public int size. We simply return our size variable. We've got that one, right? Remember we said we need to do offer, peak, poll, size, and iterator. So let's do offer. Public Boolean offer. Let's go ahead and make sure we know that. The offer method is going to return false if it cannot be added. So if we're making an expandable array, if we wanted to have a maximum size, we could say we could return false if it's too big. Or if we wanted to do some other limitation on it, but we'll do that. And this will be, I'll use E for the element. Okay. All right, so the way that we add to a heap, let's go ahead and review that, is, we have this array that's defining our heap. And this array is keeping our heap to being this complete tree here. So whenever we add to the array, we know that we're going to add right there at this bottom value, okay? And that bottom value is always going to be size. This is index 0 in our array, right? So here's our array. And that's going to be index 0, index 1, 2, 3, 4, 5, 6, 7, 8. So when we add a new thing, it'll always be its size. So I'll say if size is equal to array.length, well, we need to expand. Okay, so that makes sure we have room. Then I'll simply say array bracket size is equal to E, and we'll go ahead and increase size before we forget. Now, what do we do when this happens? Well, we need to make sure that we do not violate our min-heap rule. So we need to check and see if this node's parent is less than the current node. So we need to make sure about that. So remember that for each child, its parent is itself minus 1 divided by 2. So for example, this is index 0, 1, 2. 2 minus 1 is 1. 1 divided by 2 is 0. This here is 1. 1 minus 1 is 0. 0 divided by 0 is 0. 0 divided by 2 is 0. This is 0, 1, 2, 3, 4. Let's try this one. Here's 4. 4 minus 1 is 3. 3 divided by 2 is 1. This is 3. 3 minus 2 is 1. 0, 1, 2, 3 is 3 minus 1 is 2. 2 divided by 2 is 1. So that's the rule. The parent is always equal to the child's index minus 1 over 2. So, if you're not sure about that, you can always figure it out just by thinking about it. So that means that these need to be comparable, and we can't make a heap unless something is comparable. So we'll have to do that. We'll have to assume that that's what's being used. And if we try and add something that's not comparable, we'll get a class cast exception. So let's let's do that. I'm going to make an index. My current index is size. I'll call that child. That's my child index. So we'll say child equals size. Now, the parent is equal to the child minus 1 divided by 2. Okay? While parent is greater than or equal to 0, we'll make sure we're not out of bounds, and watch how I do this. Comparable array, I'll move this down to a new line so we can see a little better. Array bracket parent is greater than comparable. Sorry, array bracket parent dot compare to array bracket child. Now, I shouldn't have to say comparable here. I shouldn't have to cast the child as a comparable because the compare to method will do that for me. The comparable means that it has a compare to method. So I have to have this comparable. I have to cast this as a comparable so that I can run its compare to. The compare to method will handle any kind of adjusting that it needs to do to the type. So in fact, it takes an object. Compare to takes object type, so it's fine. But what we need to realize is the dot operator actually comes before the cast. So I need to do this. I need to put that in parentheses so I cast it first. So while this is happening, well, the parent is greater than the child. So if you compare A compared to B, let me write that out so we can kind of look at it. If A dot compare to B is greater than 0, that means A is greater than 0. So while our parent is greater than our child, we've got a problem, right? We got a problem because the parent should never be greater than the child. The child should be less than if the parent's greater than the child, then that child and that parent need to switch because each node should be less than its two children. So we need to switch those two. So we'll simply say we're going to swap them. So let's write a swap method. So we're going to swap child and parent. Okay, I think that will work well for us. So we'll write that as another private method down here. So private void swap int A, int B. So we'll say object temp is equal to array bracket A, and array bracket A was going to get array bracket B, and then array bracket B is going to get temp that we just overrode. All right, so that'll take care of the swapping. All right, so after we swap, though, we need to change what is our child and our parent. So our child is now the parent index because we just swapped the child and the parent, right? And then our parent is going to, again, become child minus 1 over 2. Now, that's why I have this parent greater than or equal to 0, because if this parent ever goes negative or something like that, then what we're going to get is you would get, that would go out of bounds. I'm not sure actually exactly how that would ever happen, because if child were 0, 0 minus 1 is negative 1, negative 1 by 2 is still 0. But then this, parent and child would be the same, so that would not end up happening there. So either way, it's going to stop that while loop at some point. Okay? All right, so once that's happened, we should have everything should be in the right place. And so we'll just simply return true. And there we have it. Okay, let's take a look at our next thing that we have to do. We need to do peak. So what does peak return? Let's take a look. Okay, peak is going to retrieve but not remove the headers queue, right? This method differs. Oh, that's element. We need to go to peak. Retrieves but does not remove the headers queue. Returns null if the queue is empty. Okay. So public E peak. So we're going to say if size is equal to 0, we'll return null. Else, what can we do? And I really don't need the else there because I'm already returned, but that's okay. So else, what will we do if it's not an empty queue? We're going to return the top of our queue. So we'll say return typed as an E array bracket 0. That's the head of our queue. All right, now we got to do pull. So if the size is 0, there's nothing to pull from, right? And return null. Nothing will happen. But what will we do otherwise? What will we do otherwise? So let's go back to this. When we pull, we're going to remove right from the top, right? We're going to remove right from the top, and what ends up taking its place is the bottom. Okay? So let's make sure that we do that. We're going to have to be real careful with how we do this. So I'll say E to return is equal to array bracket 0. So, and I'll go ahead and cast it as an E right now. There we go. So that's what we're going to return, but we've got to erase it. The very last element is an index size minus 1. So I'll simply say array bracket 0 gets array bracket size minus 1. So we're not actually going to be removing what's in size minus 1, but when we decrement the size, we'll definitely no longer have access to it. So now that that's happened, now we need to do the process of trickling down, because whatever we put here most likely is going to violate our min heap, and we have to choose the worst offender. So, like for example, if we put an 8 up here and there's a 4 here and a 2 here, we need to swap the 8 and the 2. So, all right, let's say int parent is at index 0. Int left child is at parent times 2 plus 1. And our right child, remember, is at our parent index times 2 plus 2. All right, so while let's see here. While left child is less than size, I guess I could just do right and right child, right? But well, so I'm thinking we got to be careful here, because if we come, let's say we have a situation where we have just one child. We could have a child here, but not a child over there. So we need to be a little careful with how we do this. We could also make a Boolean called keep trickling down, like keep trickling, and we can set keep trickling to true, and we'll just keep trickling, and we'll turn that off as soon as we're done. We could do that. We could do a while true loop that we break from when we're done. All sorts of different things we could do. But I'll tell you what, I'm going to go ahead and just say, let's try this. Let's say while true. Okay. If left child is less than size and right child is less than size. Well, I guess I don't need that then. I could just say this. Okay, I'm doing the first case. The case I'm going to look at right now is that we're at a node that has 2 children. Okay, so if the right child's less than size, then we definitely have that. And I'll say, what about if the right child is the worst offender? So in that case, we have array bracket right child So we have to make it comparable. array bracket right child. Let me put this on a separate line here. Dot compare to array bracket parent is, now they are supposed to be not smaller. You're supposed, this parent should be less than the child. So if this is less than that, and just going to copy all that, and array dot right child dot compare to array dot left child is less than 0. So in that situation, we have a right child that is less than the left child. So for example, like we said earlier, we have an 8 here. The right child is less than this and it's less than that. Then what we need to do is we need to swap those. So we will swap parent with right child. My parent index will become my right child index. And we have to reassign both our left child and our right child. Left child is equal to parent times 2 plus 1. Right child equals parent times 2 plus 2. Okay, so that should take care of the situation where the right child is what we need to swap with because it is less than the parent and it is less than the left child. Let's do another one. Else if left child is less than size, and again, I'm going to need to use this, but this time I'm using left child. Let me bring that down so we can look at it. And the array left child that compared to parent is less than 0. Now we already know that the right child is not who we should swap for. We already checked that. So as long as the left child is less than the parent, that's who we should swap for. Remember, you only swap with the right child if it is less than the parent and less than the left child. So we've already ruled out that. So we know that this is not sure where I'm missing a... Oh, I am missing... There we go. Okay, perfect. And then, there we go. Then I need to swap the left child and the parent. Parent index needs to become left child index. Left child needs to become parent times 2 plus 1. And right child needs to become parent times 2 plus 2. There we go. Okay. What else would we do? Well, if we didn't swap with the right and we didn't swap with the left, then we must be done with our trickling. So we can simply return to return. Okay. It might make me go back and handle that issue there, but because I've got a while true, hopefully it realizes that I do return at some point. Okay, well, we're not quite done yet because we got to do the iterator. So here comes the iterator. Remember the method iterator? It's public iterator iterator. And we're just going to return a new, and I usually just call it. So we got to make ourselves a little class here. Private class it. Of type E. Actually, I don't need that there. Just private class it implements iterator of type E. There we go. So the iterator has methods next, has next, and remove. The default operation for remove is that it's not supported, and that's exactly how we're going to leave it, because I don't want people removing except for from the pull operation. So we'll say int index so for no, what am I doing? It index will equal 0, and we're going to say public boolean has next. We have next if the index is less than the size, -1. No, if it's just less than size, because we're going to return the one that's current index. Public e next. We're going to say e to return is equal to array bracket index. Then we'll say index plus plus, and we'll return to return. Of course, I need to type it as an E. I could have also said index plus plus and then returned array index -1. That might have saved me a line of code. But all right, something it does not like. Oh, what does it not like here? Oh, I didn't, because I'm not returning it. Return index minus in size. Okay, let's see what it thinks. Errors, 3 errors. Okay, iterator. Oop, we didn't import. So here we go. Import java.util.iterator. The method iterator. I thought we did. Iterator. There we go. Okay. I think it likes it. Okay. So now we're ready to test it out. Okay, just a couple of corrections here. If you go back to offer, I forgot that I increased my size here, and then I set child the size. Well, I just added it at size, but then I increased size. So the child needs what we just added. So we need to say size -1 there. All right, so let's try it out. I'm going to make a new min-heap queue, and I'll give the parameter of, I'm going to say type string. Okay, and I'm going to add some stuff to here. Notice we do have a lot that we've inherited that we can use because we are using these abstract collections. We didn't write, we did not write element, remove, or add, but they use our offer, peek, and pull. So that's kind of nice. So let's do it. Let's offer the string like hello. And it returns true, just like we said it would. Let's offer another string goodbye. And now, one of the nice things about that is we wrote an iterator, and that iterator is used by our abstract queue to make a toString. So we can go, I think it's actually the abstract collection, yeah. So if we call toString, we actually see the tree. So we know that it's going to be goodbye up here. Let me get rid of all of this so we can see this here. So it's going to be goodbye here. And then hello down here, right? Because that's what the toString tells me. Let's add another word. Let's offer the word about minnow. So after adding that, and we take a look at the toString, let's see here, from object, it's in object, right? ToString, goodbye, hello, and minnow. So we G, H, and then M. As long as we use lowercase, this should be, this should always be the smallest letter, right? Well, let's add a smaller one. Let's add I'll tell you what. Let's add balloon. Okay, so we'll offer balloon. Okay, and let's take a look at that now. Go to the toString. And you can see now that's up there at the top. So it's balloon here. Then it's G, M, and H. So then G, M, and then H. Which is fine. I mean, that's not violating the min heap. H is greater than G, which is greater than B. It doesn't matter that M is greater than H. That's not a problem. Remember, it's somewhat ordered. And we can poll, and we know what will happen when we poll. We'll get the top of that list. We can peek. It'll show us, but it won't remove it. Well, you can poll. Pulls off the top of that queue, and take a look and see what it does to the toString now, and we can have a look at that toString. So the balloon is gone. So now it's, the goodbye's there. So what had to have happened was after this balloon was gone, H went up there and then came down. All right. Well, if you can add this, import this code here, which I'll include at my webpage, you can find HeapViewer. I did make some edits to it. Originally, I called this min-heap, so I had to recall it min-heap Q because that's what we called it here. So just keep that in mind. I'm using the words min-heap queue. Java calls their min-heap queue a priority queue, or we could also just call it a min-heap. But if we run this application now, we should be able to get a nice visual representation of our queue. Hopefully. Okay. So I'm not sure if we're allowed to add words to this or not. Yeah, you're not. You have to add integers, which is fine. So type integer definitely has comparable filled out, so we can do that. We notice the 13 went immediately to the top. Okay, remember we're filling out this binary tree. 12 is going to go in front of that 13. Now let's do. I'll tell you what. Let's do 14. See where that goes. No problem there. The next one, let's do 16. That has to swap to 24. Let's add it 8. See, 8 went up there, right? So we can now just do a quick toString to see that it goes just like the order of the array. 8, 13, 12, 15, 14, 24, 16. Because that's what we did our iterator. We just told iterator to start at index 0 and just keep pounding down until you get to the end of the index. So this is not going to be at all sorted, but this will be the least amount. And that's an important concept. That's a common test question that you have to make, pull, and all that stuff from a priority queue, and know that if you printed it, it would just print that level order right there. Let's pull, see how that works. There's a 12. That should be the smallest one. Which if I pull again, I should get a 13, then a 14, then a 15, then a 16, then a 24, and there we go. So I hope you enjoyed learning about min heaps and a little bit more about generics and a little bit more about abstract queues. So take care.